On behalf of 24HourAnswers.com, I welcome you to today's lesson. In this video, I'm going to show you an example of applying what's called the squeeze theorem in order to find a limit. And we have this function here, g of x equals x squared times the sine of 1 over x, and we want to find the limit of g of x as x approaches 0. Well, first thing you try to do is direct substitution, but we're going to have an issue right there, right? Because we have a 0 in our denominator. So what we want to think about is the squeeze theorem. More than likely, if you have a question like this on a test, your instructor is going to say, apply the squeeze theorem to, show that some limit does exist. Because now, if it was just sine of 1 over x, we did look at that in an earlier video where the limit does not exist, but this x squared actually lets this function behave a little bit differently such that the limit does exist. And that's what I want to show you here. But before we jump into all this, let's just look at sine of 1 over x one more time. So here we are inside of Desmos, and we have that sine of 1 over x. And what I want you to notice is that, over here, it looks like, the y value is going down to 0, and over here, the y value is approaching 0. But what I want you to notice is that the highest that sine is ever, or sine of 1 over x is ever going to be, the biggest y value that we're going to have up here is 1. The smallest y value we're going to have is negative 1. Well, that should make sense because sine, if you think about your unit circle, sine is going to be anywhere between negative 1 and positive 1. So therefore, sine of 1 over x is going to be anywhere in between negative 1 and positive 1. And this will be true as long as x is not equal to 0, because when x is equal to 0, the function is undefined. Now, ultimately, what we're going to be doing by the end of this example is I'm going to show you how this function g of x, this black curve, notice this black curve is sandwiched or squeezed in between this blue curve and this green curve. I'm going to show you how we can apply the squeeze theorem to where we can say, hey, the limit as x approaches 0 for this function here, it is going to be 0 in this case. Let's go ahead and have a look. So what I have over here is f of x is less than or equal to g of x is less than or equal to h of x. It may be slightly different notation in your text, but the g of x, I'm not going to necessarily talk about x squared sine of 1 over x right now, but what I am going to motivate here is I'm going to write that sine of 1 over x. And we looked at that just a moment ago, that orange oscillating function, and we noticed that it was always going to be in between negative 1 and positive 1. However, sine of 1 over x is not really what we're after. Our g of x is x squared times the sine of 1 over x. So let's multiply all three of these pieces by x squared. So multiplying this by x squared, we have negative x squared is less than or equal to x squared sine of 1 over x, and that's going to be less than or equal to positive x squared. I multiplied all three of these pieces by x squared, and this inequality here still remains true. Negative x squared is a parabola that opens down, positive x squared is a parabola that opens up. And this function here is still going to fall in between them, since originally sine of 1 over x is going to be somewhere in between negative 1 and positive 1. Let's look at this graph now to see this one more time. So notice I do have a x squared, my blue function, and this one's always going to be above this black curve g of x, and then the black curve is always going to be above this green curve that I've called f of x. And notice as we zoom in here, I'm going to take away these dots so you can see that. But as we zoom in, this black curve is getting sandwiched in between the blue and the green. So what does the squeeze theorem really tell us? Do you see how this black is getting squeezed or sandwiched in between the blue and the green? How do we apply the squeeze theorem? Well, what we can do with these two functions right here, let's apply that same limit as x approaches 0. So the limit as x approaches 0 of negative x squared, well, we can do direct substitution here. That is going to be equal to 0, because if we plug 0 into here, we do get 0. Less than or equal to our unknown limit, I'm going to put a question mark there, and that's going to be less than or equal to what? Well, let's do direct substitution with this same limit over here. So the limit as x approaches 0 of positive x squared, direct substitution, we get 0 there as well. And this is illustrating it without us necessarily having to look at a graph. Well, if 0 is less than or equal to something, and that's less than or equal to 0, this question mark here must be a 0. So that is going to be the limit to this particular problem. And again, let's look at that. So we're saying that this is equal to 0. Let's look at that graph one more time to make sure we can see why this function here, x squared sine of 1 over x, is squeezed in between these two functions. And since it's squeezed in between them and these two limits are both equal to 0, since this is squeezed in between it, that limit must be 0 as well. So notice again how we have that h of x that's on top of the black function, the g of x, which is on top of our f function. But notice the blue and the green, which is our h of x and f of x, is squeezing this function here. And if I hide this one here, the one that's getting sandwiched, the g of x, notice that this limit is going to be 0 as we approach 0. And also over here, this limit's going to be 0 as we approach 0 as well. Therefore, this one right here, since it's squeezed in between these two functions, its limit's going to be 0 as well. So what I want you to see here, that I've hidden the h of x and f of x, this is our original function. If I take this slider here that you see, this red dot flying around, and notice right now, I'm going to put it right somewhere in here. So our x value is 0.2, and which corresponds to this thing that I have set up over here in Desmos. But if I let this x value of 0.2 get close to 0, I want you to notice that this y value is going to get close to 0 as well. So notice right there, when x is 0.01, that y value is really close to 0. However, when we let this x value become 0, notice the dot is gone, because really the function is not defined when x is 0. And to show you that even more, let's look at that hole. So I've zoomed in quite a bit, and hopefully you do see there, when x is 0, the function is undefined. However, that limit is approaching 0. And a way that we can do that without ever really having to graph is to, take our function. If we know something about a part of it, sine of 1 over x, sine of something is always going to be in between -1 and +1, as long as x is not equal to 0 in this case. And then we just did this little trick here where we multiplied everything by x squared to make it match our original g of x. Then when we take these two functions, if we can find the limit of these, which direct substitution works very nicely here, if we get the same limit for these, and since this function is sandwiched in between them, that limit must be the same as these two values as well. And that's one example of the squeeze theorem where we can find a limit of a function that's kind of funky. Granted, we can find two easier functions that have the same limit. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.